Last talk of the day will be given by Floris from Doorn from Orsay about lessons learned from formalizing convex integration, the local theory of convex integration.
Thank you very much, and thank you, Filippo, for organizing this great meeting. Yeah, so this talk will be a continuation of Patrick's talk, where we started out today. So Patrick talked about how the theory of convex integration gave us like sphere version, and he gave like some of the analytic parts of the proof, but another part of the proof is a really geometric part that I want to focus on. And in this part, we had more trouble like formalizing the proofs, which in some of the sources were given as like a picture. See here, this picture, you can clearly see what's going on, and translating that into Lyon was sometimes some effort, but we learned some interesting things along the way. Yeah, so for the people who weren't there this morning, so the goal of this project, which I'm doing together with Patrick Masson and Oliver Nash, is to formalize sphere inversion as a consequence of like a general theory of convex integration. As Jan also mentioned, Patrick wrote nice software which can generate dependency graphs. I think the labels are slightly too small to read, but so this is the dependency graph of our whole project. So here at the bottom is a node labeled sphere inversion, and that is our final goal. And then each of these nodes is either one definition or one lemma towards this goal. And so all the green nodes are the things we've already done, and all the blank or blue nodes are the things we still need to do. And so to separate this graph out a little bit, so this is the part that I will talk about in this talk, the more geometric parts of working with loops. Then this is in addition, the second, this part is the part that Patrick talked about this morning, to get from these loops, like these approximations of the derivative, you get like a way to modify a function to have like nice derivatives. And then all this white part is to formalize one or like a couple lines of paper to show that if you can do it locally in a vector space, then well, clearly you can do it globally in a whole manifold. But the problem is that so there's a nice formalization of manifolds in Lyon, thanks to Sebastian. We're thanking each other, but there are still things missing that we need for this project. For example, one of like two things that are still missing is like the pullback of a vector bundle, or like continuous linear maps as between bundles as a vector bundle, and we need like these basic ingredients to formalize this one line of if we can do it. Yeah, so as a reminder, well, so this is the main proposition that I'm going to give a proof for in this talk. So I'm going to give this a picture. So we have two vector spaces E and F, and we have a map G between E and F. And this G plays the role of the derivative of our function of Patrick's talk at the start. So remember, in Patrick's talk, we had this function f, and we want to, in some way, improve the derivatives of f in some way. For example, for sphere inversion, we want to show that the derivatives are linearly independent, so that the function is an immersion. And so this function g here is one of these derivatives in some particular direction. which is a map between vector spaces. And what we want to do is we want to approximate this map using loops inside some specified allowed region omega. So for each of x in the domain, we have a region omega x, where we have a map data x inside omega. And what we want is we want to find a loop in omega x such that the average of this loop is g of x. And this was the key ingredient that Patrick needed for his formula to define his new f with the better derivatives. And so as part, and as Patrick explained, one of the things we need to assume for this is that G lies in the convex hull or the interior of the convex hull of the omega. So the goal of this talk is to define these loops with some conditions. These loops have to be smooth, and they have to be smooth in all variables. So they have to be like the loops have to be smooth, but also smooth as it's smooth in X. And each loop, for technical reasons, we want each loop to be contractible. So each loop also has to come with a homotopy to the constant loop, and that part, these homotopy have to also be smooth in all variables. So here's the proposition in words. So we have omega, an open set in E times F. Such that if we take these slices of the omega, these omega x, they are connected components in F. And we have these smooth maps beta and G. And we assume that beta, the base points for the loops we want are in omega x. And finally, the G's are in the convex hull of omega x. And because omega is open, we don't have to take the interior of the convex hull. And then the conclusion of the proposition is that we have a smooth family of loops, depending on three arguments: the x, which is the point in the domain, the t, which is the variable that indicates the homotopy towards the constant loop, and then it's a loop in F. So the s is just the variable how far it is along the loop with these properties. So these loops have to lie in omega x. When t is equal to 0, the loop has to be the base point. So the homotopy has to start with the constant loop, and the loops have to be based always at beta x. And these loops have as average g of x. So this is quite a large proposition to write down. And actually, I left out one more thing. We need one more condition. And that is that we're also given a compact set where we already have some, or where we have one extra condition, namely that g of x is equal to beta x in some open neighborhood of the compact set K. And so that's very easy to find the loops. But we do require that our loops are equal to beta of x, again in an open neighborhood. And so the tricky thing, to simplify, let's focus first on one specific x, because this is way too much information. So I'm going to remove the k again, and I'm also going to remove the x from the proposition, and now it already looks quite a bit simpler. So now omega is just a single open connected set in F. Now beta and G are elements of F. They have a bit of a weird name, but I keep the same name because they are functions, just evaluated at a single point. Beta lies in omega, and G is in the convex hull of omega. And now we just need for one single x, well, a family of loops, really a loop and a homotopy, such that these properties. So, oh yeah, and to simplify things a bit more, like this is just for a single point, and later I need to modify these loops a bunch. And these modifications, it's going to be hard to preserve smoothness for these modifications. So let's just start with continuous loops. And then we'll smooth them in the end. And let's also start with, instead of saying that G is the average of gamma 1, we just say that gamma 1 surrounds G in some way. And then we'll have to make sure in the end that that we can reparameterize this loop to get average G. What do I mean by surround? I mean the following. So we say that we have a point x. So a point is surrounded by a finite set of points. Means that well, first of all, these points form an affine basis. So we want them to be linearly independent and span the whole space. And it has to, we have to find positive weights with someone such that x is this affine combination of these different points. And in particular, so it's important that none of these weights is allowed to be zero, that it's really in the interior. So these points form a polyhedron, and really x has to lie in the interior of this polyhedron. And so set surrounds x if we can find some points in this set surrounding x. So this loop surrounds x if the image of the loop has these points. And here's a lemma that I'm not going to prove, and that is that if we have an open set P, then x lies in the convex hull precisely, or that implies that P surrounds x with this surrounding property. So if we have a point in the convex hull of an open set, then we can find these points and these barycentric coordinates W that surround x. And so now for the pointwise version, we can do the following. So we have this G in the convex hull, this beta and omega. And so by the lemma, we know that there's some set of points that form an affine basis, and like we have these positive weights that to form G. So we picked some set of points, and because omega is connected, now we can just start at beta and find a path through all these points. I don't need a path, I need a loop. So I need to cycle back from the last point to the first point, but I have to make sure that my loop is null homotopic. So I'm going to just cycle back exactly the way I came from. So I'm going to retrace the path back to beta, and then we obtain a path and a loop. We obtain a path which is null homotopic. Like we can clearly shrink this to the constant loop. Oh, I'm writing path. We obtain a loop that is homotopic to the constant loop. So this is the solution for one point. One problem. So now we just need to do this for every point in a smooth way. But the problem is that we had a lot of freedom in this argument. Like we could pick these points in many different ways, and we have to make sure that we pick these points in a coherent way so that we end up with a smooth map if you do this for all x at once. So it takes some work to glue all these pointwise solutions together. So everything fine so far for the pointwise story? Okay, so if you have a pointwise solution, it is not very hard to get a local solution. So if we have such a loop at x naught, so based at beta x naught surrounding g of x naught, which we got from the previous slide, then we can just linearly extend this to get a local solution. So we just change it following the base point beta. Well, so this will always be based at beta and homotopic to the constant loop at beta. And clearly this won't be a global solution, but for x sufficiently close to x naught, we will still have that gamma lies in, so gamma x, so this loop lies in omega of x. Because, well, omega x is open, so omega is open. So if we change x just a little bit, we'll stay inside. So this is equivalent to saying that x comma gamma lies in omega, and that is a continuous function. So for x sufficiently close to x naught, this will stay inside omega. And also for x sufficiently close to x naught, if we take the loop where t is equal to 1, this will still surround g of x, because we, so g of x naught lies in the interior of the loop based at x, gamma x naught. And so if we move all the points just a little bit, the g of x, because everything is continuous, g of x will still lie in the interior. So these notions are very nice to write down mathematically for sufficiently for x sufficiently close to x naught. And they might sound a little imprecise, but actually using the filter library that Patrick was also mentioning this morning, we can like state this very nicely in Lean. Again, so using these filters. So this is so here we're talking about the neighborhood filter of x naught. So these are just the collection of all sets that contain an open set around x naught. And so this quantifier says that x, so that this proposition is true for all points that are eventually in this neighborhood filter. So what is this? This is saying is that for some open sets around x, well, so that the set of points where this is true for is an element of the neighborhood filter around x naught. And so we can write this down and prove this, and then we can also write this second statement down. So these are actually actual Lean statements that translate these to bullet points above. And so we can prove both of them individually, and then we have a nice filter library that shows that, well, if eventually, so for x sufficiently close to x naught, this holds, and for x sufficiently close to x naught, this second property also holds, then of course for x sufficiently close to x naught, both of these properties hold. That is one of the rules for a filter that's required, for which you can conclude that. Yeah, so
there was a question about what is the
so this f is just an annotation to the for all to make Lean not being to tell to Lean that we are not here using the universal quantifier over x, but that we are using a notion on filters. Yeah, so this is our notion for the eventual, for that this property holds eventually for x in the filter.
So it's F stands for filter.
Yeah.
F stands for.
Ah, I thought it stands for frequently.
No, because frequently is the other one is exist.
Well, but the exists with the F, so I thought it had been copied by the other one.
No, it's really.
Because it's not capital.
The
Filter is capital.
neighborhood of x0 is a kind of a generalized subset of E. It's the general set of points that are sufficiently close to x0. And so this notation is really meant to be read to as for all x in the set of points that are sufficiently close to x0, we do have the conclusion for all t. It's suggestive notation for this.
There exists u and x0s just for x.
Yes, so it's adding a more quantifier.
Okay.
But there's really a really nice set of lemmas and rules of manipulating those things. It's very convenient to use.
Yep. Okay, so this gives us a local solution. So for each point, we get a small neighborhood where we get a local solution of these families of loops. And now what we want, oh yes, let me introduce a little bit of notation. So I'm writing gamma is an element of the script LU for such a gamma defined on some open set, or well, maybe not necessarily open set U. And so here I've written what that means precisely. So it's a continuous family of loops. Like this, with all these properties we have in the proposition. But these properties, we only assume them for x and u. And so here I'm using another trick in formalization that gamma is defined on all of E, and it's actually a continuous family of loops on all of E. But all these properties only hold inside this small set U. And this is again nice because then we don't have to worry work with partial functions. We have functions that are defined in all of E. And actually, I'm cheating it a little bit compared to the formalization. Like I'm writing 0, 1 here, but in our formalization, actually, we take a real number argument here as well. But we are just only interested in what t does in the interval 0, 1. Okay, so these are these local solutions, and now we really want to glue to multiple of these solutions together. So we have so around each of these points we get a local solution. So how from that do we get a global solution? Well, first maybe we should start with 2 local solutions and try to glue them together and get something on the union of their domain. So if you have gamma 0 in defined or with value from U0 and gamma 1 value from U1, can you get something on the union of those 2 sets? And well, for this to work, well, really I need to transition in some way from gamma 0 to gamma 1 on the intersections of their domains. And for that we have the following lemma. That indeed L of U is contractible. And the form of this statement we need is that if you have 2 of such local solutions on U, gamma 0 and gamma 1, then we have a continuous homotopy between them. So now we have a family of homotopies between these families of loops. So now we have 4 arguments. But so I want this continuous homotopy such that delta 0 is gamma 0 and delta 1 is gamma 1. And all these deltas for all intermediate parts are still a local solution satisfying all these properties. And so here's a sequence of pictures. This is from lecture notes by Franz and Borelli from here. I don't think he's in the audience. That explains clearly how to define this homotopy. And he does mention it in his lecture notes that that this is the main point of the proof, and that and points to another source for the full details. But this is all you get to define the homotopy. But so this so let's look a bit what is happening here. So so the notation is a little bit different. So the point we're surrounding here is Z, and so we have this red loop here, which we start with, which is our gamma 0, and with this blue loop, which is our gamma 1, and we need a homotopy between them. And we cannot. So the thing you might do is just well shrink the first loop down to a point and then extend it to the second loop. But what is important is that everywhere during our homotopy, we still have to keep surrounding Z. So what we have to do instead of first shrinking, then extending along the other loop is that we're first extending along the other loop. So we start our homotopy at one loop, and we first extend, we grow along the other loop. And of course, this growing we can do using the homotopy given by the second loop. And then we have the concatenation or composition of the two loops. And then we shrink gamma 1 down 2 points to get just our second loop. And everywhere along this process, we see that we are always surrounding Z. So of course, this picture, Lyon didn't really like this picture, so we had to give a little bit more details for our proof. So here is our way of how we define this in Lyon. So we've started this piecewise affine function, which is the one for from R to R. So if the input is less than a half, we're 1. If the input is greater than 1, it's 0, and it's linear between them. And now we're saying, so this tau is how far we've moved along the homotopy between gamma 0 and gamma 1. And we're saying first move along gamma 0 between 0 and 1 minus tau. And then move along gamma 1 for the remaining part of your interval. But we're doing something funny with this argument on the top, which is so this argument on the top is the argument that defines the homotopy of gamma to the constant loop. So what we're doing here really is so for tau less than a half, rho is 1. So here, if you look at delta 1, yeah, so maybe if I write this, so for tau less than a half, delta 1 of tau x is just gamma 0. Well, moves along this loop first, and then it will move along the second loop. And here we use rho 1 minus tau. So if tau is less than a half, rho of 1 minus tau is slowly increasing from 0 to 1. So that captures that we're increasing like how much we're covering of the second loop. And then for tau greater than a half, we're slowly shrinking this gamma, what we're moving along gamma down to the constant loop, and we are keeping this constant. And that is for t is equal to 1, and then for t less than 1, we're just taking multiplying the top argument by t to shrink that whole process down to the constant homotopy. And we're doing something. We're just doing the linear parts, in this part, we only have to move a little bit along gamma 2, so we only spend a little bit of time doing that for small tau. So now, so this does capture the intuition of this previous picture, and now we have to prove the properties. So first of all, does this surround the points? In our case, does it surround? Oh, this should be not beta but G. So we still have to make sure that we surround Q of X, and that is true because our homotopy always contains the image of either gamma 1 or of gamma 0 at 1 or gamma 1 at 1. So that is true. And there's a second question: is delta continuous? Well, we have to make sure that in most places this is fine because we're only doing manipulations with continuous functions. But there's something tricky happening, for example, near tau is equal to 1. because near tau is equal to 1, we're moving along this second loop in a very short time. And so we're moving at a speed that tends to infinity along this loop. So actually to show that delta is continuous at tau is equal to 1, we had to show that this loop uniformly tends to the constant loop as these arguments tend to these values. But that is all fine because because we are only talking about a loop, so we only care about an interval, and the interval is compact. Because it tends to this value pointwise, and the interval is compact, we can show that the uniformly tends to that value. Yeah, so later we actually found out that there is a different way of defining this delta that avoids this problem. And we don't have to worry about this uniform convergence. So we were surprised that we had to work with uniform convergence to show that this quite simple construction was continuous. But this also shows that which definition you take of delta can matter for how complicated it is to prove something. To prove that it's has nice properties. Yeah, so here this is how it looks in Lyon. The same statements. So we have so if you have two loops gamma 0 and gamma 1, or family of loops that live in U or live in LU, so have all these nice properties. This is this gamma I call delta in the slides, but then there exists an homotopy between them, such that for all tau, this homotopy still lies in LU, and at the boundary points it has the correct values, and it's continuous everywhere. So this up arrow is some notation to just say gamma is continuous in all its arguments simultaneously. Okay, so now we've shown that the loops with these nice properties are contractible on open set. So how do we get from that a solution? How do we extend a solution if you have two solutions? So now we have a local solution gamma 0 on U0 and gamma 1 on U1, and we want ideally we want to get a solution of all U0 union U1, but that's actually quite hard, especially if we also want that our new solution extends our solution on U0, say, because we cannot really ensure, for example, at this point that here we all keep gamma 0 everywhere, and then near this point suddenly, or near this whole boundary, we can sort of smoothly transition into our solution of U1. So we won't be able to get a solution of all of the union. But what we can do is we can pick two compact sets in each of U0 and U1, and we can get the solution around near the union of these two compact sets. So what do we do? So we pick our first compact set K0, and from our second compact set we remove the intersection with U0, and so we have a compact subset. Assuming that U0 and U1 are open, which I'm assuming here. Then we can find neighborhoods of these compact sets, and we can find a transition function so that are still disjoint, of course, and then we can define a transition function between that is 0 on this set and 1 on this set. And now we're going to define a new solution on all of this red part. So on the neighborhood of K0, the neighborhood of K1, minus U0, and on the intersection. And we're going to define it as follows. So we can take delta as the homotopy between gamma 0 and gamma 1, which we obtained from the contractibility on L of this intersection. And then we can define a new gamma on this red region by taking delta that's where tau is equal to rho of x. So tau is 0 in this region, tau is 1 on that region, and it transitions on between 0 and 1 on the red region. And it's at the same point x. And so this will be a valid solution because delta has all these nice properties. It is a homotopy in L view. And what is interesting here is that on our previous slides, I only, if I go back, okay, I have to go back a bit far, but I only proved that delta lies in L view, so it only lies in L of the intersection of our two loops. But actually, this function has the right value on the whole red region because on this red region, rho is equal to 0, and so this delta will just be gamma 0, and on this red region, rho is equal to 1, so this will just be gamma 1. So even though we define, we show that delta has the nice properties on the intersection of U0 and U1, we get for free that it has the nice properties everywhere in the shaded region because of its interaction with rho. And so here we get some benefit out of defining our functions everywhere, and because of a lucky interaction of rho and delta, we get that it has the nice properties even outside of its original domain where we proved its nice properties.
There is one case where it's simpler when it's formalized. There's one paper what I've written originally in the blueprint was a case distinction between 3 domains, depending on whether you're on the left, in the middle piece, or on the right. But indeed, it was needlessly complicated.
And so, yeah, so what we've finally shown is that if you have two solutions, gamma 0 and gamma 1, on UI, which are neighborhoods of a complex set Ki, then we can find a solution not on all of U0 union U1, but at least in the neighborhoods of this the union of the compact sets. And also important is that near K0 is exactly the same as gamma 0. Gamma 0. And so this is the gluing two of these loops together, and now we can iterate this. We can perform induction to get from all these local solutions to a global solution. This still takes quite some work in Lyon, but the argument follows. The arguments are not too hard. So if we have, if you start with this solution gamma 0 in a neighborhood of this compact set K we started with, then we can find a global solution on all of E. So now this is really defined on the whole vector space that agrees with gamma 0 near K. And so what we do is what we can do is we can, of course, locally for every point find a local solution, and now we can restrict these local solutions to obtain, first of all, just a countable collection of these local solutions. And we can get compact subsets of these domains, such that the compact subsets cover all of E. And finally, we also need that these UI are locally finite. So every point only intersects finitely many of these open UI. And so this to get this precisely requires a combination of a couple different lemmas in the library. So we can obtain this from the shrinking lemma, and we needed to combine a couple different things, but let me not get into that in detail. But if we have this, then we can repeatedly glue all these gamma I to gamma 0, and then we can obtain a sequence of these families of loops. And because of our property that if you're near the k, so our previous lemma states that our loops, the family of loops near our compact set is equal to the old value. This on all the ki we are just extending the loop. So so we can so this sequence of family will be eventually constant in each of the ki. So namely after I steps it will be constant in ki. And so an eventually constant family of loops has a limit, and that limit will be continuous. Because continuity is a local property. So that is the induction argument. How am I doing? 15 minutes. Okay, so this finishes the proof, except that it doesn't, because I made two simplifying statements in my proposition. This only gives a continuous solution, but we want a smooth solution. And this only gives a family of loops that surrounds the point we want to have. But we don't just want to surround it; we want to really make sure that our loop averages to that point. So the smoothing takes a little bit of thought how we get it. So we have a continuous family of loops. Now we want to find a smooth approximation to it that keeps all these nice properties we want. And at first, what we thought that we could do is we can take a convolution with just some small bump function and, well, convolutions with a smooth function that gets a smooth function. But that turns out to be a bit tricky, because if you take a convolution with a smooth function, you will lose these exact equalities. Like you will get close to beta x, and you will get a loop based at some point close to beta x. Because beta moves around when x moves, like we won't be able to get a family of loops that is exactly based on beta x. And so okay, we don't have something that is exactly beta x. We can solve that by doing a partitional unity argument. We just transition from this smooth solution to the map that is at the correct values for t and s is equal to beta x, and that works, except that if we take a partitional unity argument, we actually don't need a convolution argument anymore. So in fact, we can just do it using a partitional unity argument in the following form. So if I have a map, so this is a lemma we proved using the partitional unity that Patrick proved, and this is really the idea that gives you partitional unity gives you, namely that if you have some convex property and you can find local solutions, then you get a global solution. So in this case, we have a continuous function f, and we want to approximate it with some C infinity function such that the distance between this approximation and f is never more than epsilon apart, but epsilon may depend on the point where we are. We get a smooth function that is never far away from f, specified by epsilon. And moreover, if f is already smooth near some closed set C, then we can choose our G in such a way that it coincides on C with f. So this is lemma we can prove using the partitional unity. And using this lemma, we can precisely get what we want here. We can find a smooth approximation, and we can make sure that for certain values of T and S, it is really equal to beta. We have to still do a little bit of work. We first need to reparameterize gamma so that for T near the base point, for T near 0 and for S near the base point, we actually make gamma constant. But we can do that because we don't care about the precise values of T and S near those values. And then if we then make gamma close to these points equal to beta, and because beta is smooth, we get something that is near these points already smooth, and so we really get these equalities as we want. And by saying that our smooth approximation lies near our function, we can preserve the property that it surrounds G and it stays smooth. Amazing. Okay, so that gives us a smooth solution, but now we also need to reparameterize so that the average is exactly G. I won't give this argument in detail, but the idea is as follows. So for a single point, we have this loop around G, and this loop, and we know by assumption that this loop surrounds G. So we have these points such that G is in the, G of X is in the interior of the polyhedron defined by these points. And now what we can do is we can just reparameterize this loop so that we move very quickly from the base point to the first point. We stay, so we compute the barycentric coordinates of this point compared to this polyhedron. And then we stay at this point, we just stand still for a time that is approximately equal to the barycentric weight of this point. Then we very quickly move to the second point, and we stay at that point for a while. We continue with that. We still have to take some care to do this in a smooth way in X, and then the formula gets quite tricky, so I will skip that in this slide. But actually, in that proof, we still use the convolution because we want to take the convolution of gamma with some small functions that approximate a direct delta function at these particular points. And that gets me to the last topic of my talk.
At the end of this argument,
yes.
It's a limit of path, or it's a intermediate value theorem to get this.
No, we can get it exactly. The reparameterization.
There is a non-trivial ingredient that is not explained. It's not like just how to go from what is said.
Yeah.
Explain that.
Yeah, yeah, there's still like quite some work done to make it sure that this is smooth in X.
Si tu prends juste la limite, tu trouves une fonction qui est discontinue, et tu prends quelque chose d'autre. Je te raconte.
But so in the last part of my talk, I want to talk a bit about convolution. So which we first thought we would end up using for the smoothing argument, but in the end we ended up using it for the reparameterization argument. So in the original form that I wanted, the convolution was as follows. So we have a function from a vector space with real numbers, and a function from between two vector spaces, and we want to define the convolution. Which is a new function from E to F, which is given by the usual formula, except that I have to choose, as in Sebastian's talk, I have to choose some higher measure on E. And so then we take the integral over all of E of F, and then it's shifted and flipped G, and multiplied together. And so really the application I had in mind is to start with this G and now approximate take the convolution with a smooth bound function to get a smooth approximation of G. So that's why F takes size in R, we get the scalar multiplication of vectors, vector value function G. And I did this in the generality where E is a topological abelian group equipped with a Haar measure, and F is an arbitrary Convex space, not necessarily finite dimensional. And then we can prove, we want to do this where F is a smooth bump function. We want to at least apply it to that case. And bump functions were defined by Yuri in Lyon. So we have those, so that's nice. And this has some nice properties. So, for example, if we have a sequence of bump functions f that tends to the Dirac delta function, which in this case I just mean, so these functions have integral 1 and their support like shrinks down to a small set around x naught. Then the convolution at x, or the convolution just tends to a constant function, g of x naught. And I also want that the convolution is smooth. So if f is well Cn and has convex support and g is locally integrable, then the convolution is also Cn. So and in the proof of this property, if I look at some books proving this, what is interesting is that all the books that I could find and that I could find together with Patrick, we looked at a couple of books and they all show this by computing its partial derivative. So we take the partial derivative of the convolution and we can take this partial derivative inside the integral and we can show that it's equal to the partial derivative of f and then take the convolution of that with g. But
sorry, can you get back to the definition of the convolution that you so this
so E here can be
yeah, so my question was what
does not need to be like one dimensional, right?
But still R needs to be R, the real numbers.
Yeah, so in this version R still really needs to be real numbers because like I need to multiply these functions in some way.
Yeah, like in any ring.
Yeah, but I also need to take into I also need to take an integral.
Yeah.
I don't think that our
no, it's really useful. I mean, this is something that would be very useful.
I don't think that our current version of the integral works for the periodic numbers.
No, but if you want, my question was, so you need a Haar measure, okay, so that your integral makes sense. And you need that you have a multiplication by where I mean you have a smooth of where f takes value. The type where g takes value has a multiplication by where f takes value.
Yes. Well, but the integrand has to live in a Banach space, at least in the current definition of integral.
I have a question on this formula definition. Is it important that the E is abelian?
So no, and in fact, when formalizing these facts, I prove actually for each result, the arguments on E and F are all slightly different. So I define this without assuming that E is abelian or even a topological group. It's just the fact that it has some subtraction operation. But for some of its applications, I assume that's abelian. But indeed, I think for the flipped version of this version, I don't need that it's abelian. Like to show that if G is smooth, then the convolution is smooth. I don't require that E is abelian at all. But I think for this version, I might need that it's abelian. But or then maybe I need a different arguments. But so some parts of the theory are more general than what I wrote here, and I don't assume.
And these are in MATLAB or in the computer version?
It's currently a pull request mode.
Okay.
Okay, so I talked about partial derivatives. So we can compute the partial derivative of this convolution. But if you're a geometer, you might ask, well, why do we work with partial derivatives? Why don't we compute the total derivative of this convolution? And this happened in none of the books we looked at. But it's also a little tricky. How do we even state this? Like the total derivative of the convolution. So this should be a linear map from at the point x should be linear map from E to F. And we want to express it in some way using a convolution of the total derivative of F with G. But the total derivative of F takes values in the dual space of E, and G takes values in F. And now none of these functions are scalar valued anymore. So how do we even state this? Like, how do we even take a convolution of these things? So the solution is, of course, to generalize the definition of convolution to also allow cases like this. And that also makes it a lot nicer, because here we have an ugly asymmetry between F and G, that F is scalar and valued and G is vector valued. And so the new definition of convolution is that F and G are both vector valued in some Banach space, or actually even I think, well, in some cases you need a vector space. For some results you need normed vector spaces, F1 and F2, and we have some continuous bilinear map L that takes works from F1 to F2 to F. And then we can define the convolution of F and G with respect to L, given by this formula. So it's the same as before, except that instead of multiplying F and G, we apply the linear map L to these two arguments. And this is exactly the same properties as before, the same nice properties of convolution, like it's still distributive, linear, associative. Associativity requires some work to even write down, but we can still prove that the convolution, if one of the functions is smooth and the other one is locally integrable, then this is still smooth, assuming that one of them has compact support at least. And well, we can now compute the derivatives.
So to be sure, E is an equal platform. Or what is this information?
Well, for the definition of convolution, it just needs to be.
No, but you talk about derivatives. So
yeah, so if we compute the derivative, then it is I assume it's a normed group over the real numbers. So this is not connected to the manifold library yet, so we're not talking about the to the computed derivative, I need to define a new linear function that takes as arguments. So all the humps are here continuous linear maps, and it takes an argument in this space of continuous linear maps and an argument in F2. And it gives a new continuous linear maps, and it's defined as this way. So it's you just compose M with the first argument of L, and this is again a continuous linear map. And now the theorem is that if F is C1 with compact support and G is locally integrable, then the total derivative of this convolution of F with G is the total derivative of F convoluted with G using this new linear map. And let's see that this makes sense. So the total derivative of F with G has to be a linear map from E to F, or at least evaluated at a point X. And this evaluated at a point X, well, here dF is evaluated at a point is a homomorphism from E to F1, a continuous linear map, and G evaluated at a point lives in F2. So indeed, this makes we can indeed, so L prime has the correct type to take this convolution with. So this statement makes sense. It type checks, but we can actually also prove it. And the proof is the same arguments as you normally prove for partial derivative, for computing the partial derivative of a convolution. So the total derivative of the convolution is the total derivative of the integral. Then we can move the total derivative inside the integral. And now we have the total derivative of a composition. Note that we only take the total derivative with respect to x. So the second argument of L is constant. So we have here by the chain rule, we take the derivative of this linear map L, which is just the same linear map, and then we take the composition of the total derivative of f. And then we can use L prime to rewrite this a little bit, which gives us exactly this expression of the convolution of the total derivative of f and g. Of course, I have to check a little bit a property to be allowed to take the total derivative inside the integral. I have to check that the integral is dominated by an integral function. But that is fine because I assume that f has complex importance and that g is locally integrable. So it's in particular integrable on the support of this integrand. So that is all fine. So let me wrap up. Do I have time? No, let me skip the lean versions of these the theorem. So as conclusion, we can formalize tricky argument in differential topology, but we do have to specify quite a bit more details than just drawing a picture on paper. Hopefully, like in like a couple more years, we will get better automation that at least helps us with the trivial proofs. But also in this project, we noticed that Lean can help us and to motivate like interesting generalizations of the concepts, so that we can, for example, compute the total derivative of a convolution. So thank you very much.
Other questions for Floris?
Yes, both you and Patrick mentioned that passing from the local, so RGBN situation to manifold one is tricky to globalize it. So, but my question was, is it tricky because you need to do it properly, or is it tricky because you have to formalize it and the manifold library is hard to work with?
I think the true answer is we don't know how tricky it is, and we don't have enough ingredients in our manifold library to do it yet. And so at least at the current moment, it's tricky because we need to still develop more of the differential geometry to be able to do it. And once we have that, I think it will be more work than on paper to do it, but like significantly, but I think it will be doable. Like I don't think it will be the majority of our work. But at that point, I will be able to properly answer the question how tricky it will be.
I mean, the main blocking point is that the manifold part of MATLib is not yet enough developed. And we can't even state the final theorem. I'm not talking about sphere version we could state, but the big theorem that implies existence of sphere version, the abstract things about maps between manifolds satisfying any kind of first order condition. We cannot state it because we don't have manifolds of jets of maps from one manifold to the other. And this is in the graph that you showed at the beginning of the talk. Many of the missing pieces are rectangles, so it means there are definitions, but there are definitions that require work. I mean, when you said there is missing a pullback of vector bundles and bundles of linear maps within vector bundles, stuff like that, there are things to prove. But we hope that once we have this should be rather easy to finish. But really, manifold is by far the most challenging thing to formalize we've made so far. I mean, the perfectoid spaces or condensed sets are much easier because of the fact that in manifold theory you've got functions that are only partially defined everywhere. And all these coordinate changes, they are defined at intersections and open sets and stuff, and this is painful with using the foundation that we use. So that's the main concern. But what we've seen in this talk that is not painful is all those arguments. So maybe it was a bit technical, especially at the end of the day. But what you should remember is that all those arguments with a compact set inside an open set with maybe a button function in the middle or a locally finite covering and then go from one set to the other. All this works really nicely when you want to formalize it, but manifold is more difficult.
Any other questions?
Late and it's hot.
Yeah. Yeah.
So maybe let's thank Floris again.